Hello YouTube. In this video I will show you how to model a reinforced concrete framed multi-story structure subjected to earthquake in ABAQUS. I will show you how to run the analysis and how to view some results as well. So if you are interested in modeling of reinforced concrete in ABAQUS, which of course doesn't have only one way to do it, but this is one of the ways to do it, or if you are interested in how to model seismic loads by means of accelerograms, you should stay tuned. So let's begin and take it step by step by creating our parts. We have a part that we will name concrete beam, and it's a solid 3D. Yes, approximate size we write here 3000. We click continue, and here we will draw a square with this tool over here. Just click on 2 points, doesn't matter, just draw some rectangle and then we are gonna dimension it. So we will say that this side is 300 and this side, vertical side, is also 300, and the units that we will use along this video will be newtons millimeters. So these 300s are millimeters. We just click done, we are done, and we are asked to write the depth of our solid element here, and that would be 2800, so 2.8 meters. So our reinforced concrete beam, as we named it, it's 2.8 meters by 30 centimeters by 30 centimeters, and click OK. And this is our element. Now we defined another part that we'll name rebar, and this will be wire element. The rest remain the same, so wire here. Alright, click continue. We just take this tool over here, polyline, and just connect 2 points, any 2 points, and like that. Take again the dimension tool, click on the first point, click on the last point, and the distance here will be 2800. Okay. Now we click done, and this is our rebar. To go now into the materials, we will have one material that will be, let's call it C2025. This will be our concrete. So general density, the density of the concrete, because we work in Newton millimeters, we know that Newton per square millimeter is megapascal, of course. So when we have stresses, they will be in megapascals. And here the mass density, because we are using these units, should be in the mass density should be in tons per millimeter power 3. So tons per millimeter power 3. This is 2.4 multiplied by 10 power minus 9. Alright, and then we have the mechanical, elasticity, elastic. The Young's modulus for concrete is 20,000 megapascals that we use here, and Poisson ratio 0.18 is the value that we use. Okay, now further we choose plasticity, and here we choose concrete damage plasticity. In this table here, we will use the default values for each of the variables, and here will be 31 degrees for the dilation angle. The eccentricity is 0.1. The ratio FB0 FC0 will be 1.16. Capital K will be 0.667, and the viscosity will be 0. And now the compressive behavior, we will just define the yield stress of 25 megapascals for the starting of the yielding plateau. So 25 megapascals and 0. And for the tensile behavior, we will just define 2.25 and 0. And this is one way of modeling concrete in ABAQUS by this method, concrete damage plasticity. You can also do it more detailed by using this this method, and I obtained this graph by this formula here, where F0 is 25 megapascals, E0 is 0.22%, E mean 0, and E max is 0.35%. The range where I defined the function. And you can see I have some values here for stresses and strains for the compressed part, yes, and also for the part in tension. I have some values. This equation is valid for the compressed side, and for the tensile fiber, I just took a bit less than 10% of the compressive stress. So and then I just defined the tensile softening in a way that looks like that. So you can also define it like this, but make sure that you only define the inelastic strains in ABAQUS, because you don't have to define the total strain. So if you want to do it like this, I just marked with colors what you have to put in ABAQUS. So again, the curve is drawn on this graph with total strains, both for the tensile, for the compressive stress strain behavior, and for the tensile stress strain behavior is drawn with stress and total strain. But in ABAQUS, if you want to describe the same phenomenon, you have to use the inelastic strains or plastic strains, and the inelastic strain is the total strain minus the elastic strain. All right. Okay, so these are the inelastic strains for the compressed fiber. So if I want for the compressed behavior, so if I want, I can just take this and then I go here, compressed, and then I delete this, and then I paste my rows. So I have this. So, and in the same way you can do it for the tensile behavior. But you will see that you use this method that if you have something more complicated than a concrete cube, then usually it's not a good thing to do. The problem is with this softening area here and here, that if the structure gets complicated, then it's really hard to obtain some results. But you can try and see what you can do. Maybe you have a supercomputer, so that might help you. I don't have a supercomputer, so for this exercise is a very used approximation to use this kind of behavior. So we only define 25 megapascals here and 2.25 megapascals here. I will come back to this file a bit later. You don't have to worry. The link to this file will be in the description, so you will have it. No problem. Okay, now we go back to ABAQUS and we just delete this. Clear table. And we can just write here back 25 megapascals and 0. And for the tensile behavior, 2.25 and 0. And that's it. We just click OK. OK. Now, let's define the steel. Materials. Steel. General density, again in tons per millimeter power 3. So that is 7.85 multiplied by 10 power minus 9. Elasticity, mechanical elasticity, elastic. Young's modulus is 210,000 megapascals or 210 gigapascals, and Poisson ratio 0.3. And we click OK. No, we don't click OK. We have to define the plasticity as well. Plasticity, mechanical plasticity, plastic. And yielding stress, we just choose 350 megapascals. So the plastic strain will be 0 for this value. Okay. Maybe to make another mention about plastic strains and inelastic strains. about elastic strains and plastic strains. Plastic strains, which are the same as inelastic strains. If you are in one point, which is right here, let's say this point. So you want to know the inelastic strain in this point. You just have the total strain, which is right here, which is about 2.2 per mile. And you want to subtract the value obtained by unloading along the Young's modulus. Right, like this. So you will have this part, the elastic part of the strain, and what will remain when you subtract that from the total strain will be this part, which is going to be the plastic part of the strain, or the inelastic strain. And how you will do that, you have simply, for this point, as you were talking about, you have this point here for the strain, and you will have the total strain minus 24 divided by 20,000. So you have the total strain minus the total stress divided by Young's modulus. This is the way that I obtained this inelastic strain, by knowing the total strains. Okay. And now going back here, we have this yielding stress and plastic strain 0 for this point. So much easier to define steel than concrete in ABAQUS, which is, of course, normal to beat. And then we click OK. Next step is to define our sections. So double click sections, and we have a solid section that we will name concrete cross section, solid homogeneous. Okay. The material is C2025, and everything else remains the same. We click OK. Now we want to define another section. Actually, we don't want to define another section yet, because we have to define a profile first. So we double click profiles, and we name the profile circ. You can see that you have some options here. We are going to choose circular, continue, and the radius will be 7. So maybe it's time to make a short description of the model that we will use. It's a multi-story frame structure that will look something like this at the end. This is how it will look. So 1, 2, 3 stories, which are exactly the same. The elements are the same. The height of the story is 2.8 meters, and the span of the beams on both directions, the clear span, is 2.8 meters. So basically this element of 2.8 meters that we defined as the beam, we will use it absolutely everywhere to construct this kind of structure. And every element will be reinforced with 4 rebars of 514, right? So 4 rebars of 514 for each element. Okay. So the radius is 7, because it's 514. 14 is the diameter of the rebar in millimeters. Okay. Now we can define the other cross section. Double click section and choose beam. We name the cross section rebar cross section, and continue. The profile name is circ. Yes, as we defined before. The section's Poisson's ratio is 0.3. We define the Poisson's ratio for steel in the material box right here, but we are just gonna define it again here. If we are asked, we will do it. All right. So that's it with this. We click OK. We go for beam section values are missing. Oh, material name. Okay, we just choose steel here. Very well. Don't forget to choose the material. And now OK. Alright. We proceed, and now we have to assign the sections to our parts. So in concrete beam, click over here. We have section assignments, double click on the beam, we click done, and we choose here concrete cross section, and we click OK. And you can see that it changed color, so the material has been defined, or the cross section. Now we go to the other part, to the rebar, and we will also define the section assignment here. Click and click done, and here it's rebar cross section, and you can see that it's the only one available here. And before, for the concrete beam, it was also the only one available because this one is a wire element and the other one was a solid element, so it was the only one available anyway. So we click OK. Alright. What should we do next? Next, we will start building our instances. So we go to assembly. Maybe we should save it here. It's a good moment to save our process. Alright. So now if we go to assembly, instances, we will choose concrete beam and rebar. Take both of them. And we will click OK. Very well, and we will start with a column. So what we will do first is that we will rotate instance here, this, and done. Select the start point for the axis of rotation. We select this point, and then point this point, and the angle 90 degrees, and click enter. Alright. And always don't forget to click here OK after you submitted the command, because if you just click escape, you will lose it and you'll have to do it again. And I will not show it to you right now what happens if you click escape. Just try by yourself if you want. Okay, and right now what I will do is I will just move a corner of this column in the center of the system of coordinates. So I will choose translate this, done, and I will move this corner right here, and again click OK. And I think middle click works as well. I just like to click OK. And actually I don't want it like this, I want it more like, again I click on translate instance, click on the instance, done, click on this point, and then click on this point. And that's exactly how I want it to be. Okay. Let's refresh the view and do it like this. Okay. Now of course I want to translate this one too and rotate it first of all. So we choose rotate, we rotate this one, done. Select the starting point for axis of rotation and we will rotate it against this axis 90 degrees. Very well, and we will move it. Initially we will just translate it. You see, I didn't click OK, so I have to do it again. So let's do again rotation. So rotate instance, I click the instance, done. Rotate around this axis 90 degrees by default here. Just click enter and then click again enter, so it's okay, it's in this position. And now we are going to translate it. Click on translate instance, translate the rebar, done. We are going to take this point and move it in the center of the system of coordinates for the moment, and click OK. Alright. What we will do now is that we will suppress the concrete beam for a moment, and we have this rebar here that we see it very clear, and we will translate it. We will translate it, and before we translate it, we will do a linear pattern. The concrete covering of our section is 30 millimeters, but it's 30 millimeters of clear concrete. So the covering from the extreme concrete fiber to the edge of the rebar is 30 millimeters. This means that from the extreme concrete fiber to the center of the rebar is 37 millimeters, right? So if that distance is 37 millimeters, if there are two coverings of 37 millimeter, it means that the distance between the rebars will be 226 millimeters. Exactly, 226 millimeters, which is basically 300 minus 37 minus again 37. I will just do it again fast on the calculator to make sure it's alright. 300 minus 37 minus again 37, it's 226 millimeters. So we are gonna click here on the linear pattern and select the instance to pattern, click done. Spacing has to be in the range. Don't worry, we will fix the spacing. The spacing is 226 millimeters, and here is also 226 millimeters. And let's fix the directions. The direction for this one is x-axis, and the direction for this one is the z-axis. And now we are sure that we created 4 rebars that will reinforce our column, and the distance between the reinforcement is exactly 226 millimeters from the center of the reinforcement to the center of the reinforcement. And now we can click OK. But we know that at this point here in the center of the system of coordinates will be the corner of our column. So we want to translate all these instances here, starting from this point, and we will go on X, we will go 37 millimeters, on Y we will go 0, so we don't change anything, and on Z we will go again 37 millimeters. Okay, so now we moved it, click OK, we moved it exactly where we wanted to put it. At least this is the best way that I find to model reinforcement for concrete, to put it exactly in the place that I want. And now we can resume our concrete beam instance, and we can also check some views so we can see that we have the reinforcement inside. Okay, we have this step, but now we have to actually to embed our reinforcement in the column. So for that we will go to constraints, and we have here, well, let's just write embedded rebar, and we choose embedded region, continue, select the embedded region, and we will choose, select the embedded region, and we will choose, maybe we should for a moment to leave the concrete beam as suppressed, and just what's the smartest way to do this? So again, go to constraints, and say embedded rebars, embedded region. Okay, select the embedded region. This is the embedded region, done. And then select method for host region, select region, and then I want to resume this, and select it, but it doesn't work. Okay, so it doesn't work, but it's no problem. We will just define some sets. So we go to sets, and we have the set, let's call it rebars, and we continue, and now we suppress the beam, and okay, go to sets again, sets, and we have rebars. We continue, we select everything, done, and we have our set. And now we can just resume this, go to constraints, embedded rebars, we continue, select the embedded region, and the embedded region is sets, and it's rebars, highlight selections in the viewport, and we can see it, continue, select method for host region, select region, and we will select let's click select in viewport, and now this is our host region. You can see it is with magenta right now, and done. And everything here we will just leave it as it is. We'll just click OK. Okay, so finally right now our rebars are embedded in the concrete. Very well. The next step is to apply a linear pattern. If we go again into assembly module and save it again, save, very well, and we will apply a linear pattern of these instances, and we're going to click done, and the offset will be 2800, which will be on X direction, and 2800 will be again on the Z direction. Okay, but now let's think a bit if this distance here is the right number that we have to write. So we want the clear span to be 2800. So if we write here 2800, then it's gonna be from this point to this point 2800. So the clear span will be only 2500. So what we want to write here to have the clear span 2800 is in fact 3100, and that goes here as well. So right now we know that if we take one of these elements and we rotate 90 degrees, it will fit exactly in this space right here. Okay, okay again. Yes, so now it's starting looking like something. What we will do right now is that we will take this column here, we will rotate it, or maybe not, no. We will do just a pattern, a linear pattern with this column over here, and we click done, and we just want one somewhere, doesn't matter where, 2000 here. Okay, we just want to keep this here for the moment because this will be rotated 90 degrees, done, 90 degrees, rotate. We can just click, or maybe not, maybe we should rotate it more smart from the beginning. So rotate instances, done, and just take this line over here. and X because we click translate instead of rotate. This instance, done, and we choose this line over here, 90 degrees. Okay. And now we will just try to bring it to the same level as the columns, so we will translate it, done. We will take it from here, and for the moment let's just leave it here. Okay. Okay, and now translate it again. No. Or maybe just try to construct it from now. Let's translate it. Done. Let's take it from here. Bring it here. Okay. Yeah. And now let's duplicate it. Linear pattern. Done. We don't want nothing here, and here on the direction. This. Flip. And here we want 3, 1, 0, 0. And now we have it there. But let's make one more. Click OK. We rotate it. Click on rotate. Click the instance. Done. We want to rotate it 90 degrees along this axis. Okay. Okay again. Translate. Instance. Click on the instances. Done. Select this point over here. And then this point over here. Okay. And now linear pattern on this instance. Done. We only need one to define the direction. Is this direction? Okay, and the distance is 3, 1, 0, 0. Okay, okay. So now we have one story. Oh, it's so great, but this is not exactly well because the beams are not tied to the columns, which is something that of course we need to solve. But for the moment, let's just construct the other two stories. So we just pattern everything. Done. We only need one pattern, and we go on this direction. And let's say 4,000. And twice. Twice, or 3 is the total number of the pattern. Okay, we leave it like this for the moment. You will see why. Okay. Also, what we want to do right now is to take out just outside, to put them aside, like here. We want to put aside the beams in order to be able to define this surface is here and this surface is here. So then we are going to put them back, and then we can apply tie connectors with respect to our previously defined surfaces. This is what we want to do. So let's try to do it. Okay. I'm just going to have a bit of water. And now we can keep going. we will translate instance, and we will select this instance here, and this instance here, or you have to hold shift when you do this. Done. Very well. Now I'm choosing the starting point of the translation vector as this one, and the end point, this one right here, and I will click OK. And now if I want, I can, come on, I can translate again if I want a bit more space. Select this, done, and I will move it just a bit farther. And we can see that something went wrong here, obviously. Some rebars didn't move, so we just click on the X. So we will just try to take it exactly from the limit. Translate instance. Maybe it's fine like this. Let's try to leave it like this for the moment. I think it's going to be fine actually. Yeah. Or maybe not. We can just select it like this and it will work. So translate instance, we select like this, we select like this, holding shift, never forget to hold shift. And remember, it's quite important when you select, or no, just forget it. Select with shift. I thought it matters if you select from left to right or from right to left, but it seems like it really doesn't. You know, in AutoCAD it does, but here, yes. So let's translate, selecting this one and holding shift, selecting this one, and we click done. Then we can go in this view, and we are just gonna translate it just a bit. Okay, so we click OK, and now we are fine. Now it looks a bit as we want to look. And the reason for which here you can see that the columns are fully connected, there are no spaces, is because here the ties between the columns have been already assigned, but here they are not. So we have to define some surfaces, and we will define 4 surfaces. But after defining any surface, we will apply some partition planes. And we go here, just don't get scared for this many instances, because it's the way to go. We will go to let's collapse this a bit so we can see something. Yeah, so it's right here, right? Partition cell, define cutting plane. We're just gonna click on that, and we have select the cells to partition, and we will click on this cells. Or no, not yet. We will not do that yet. Okay, right now let's define the surface so we can tie the columns to the columns again. So we have surfaces, we have column top surf. Okay, column top surf, continue, and select the regions for the surface, and we select the top of the columns. So we have this one here, 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 and this one here. Remember to hold shift, and it's done. And now this one, it doesn't get tied to anything, so you don't need to select it. And now we have the bottom column, so we go again to surfaces and we say column bottom surf, and we continue. We go here and select this one. Remember to hold shift, this one, and here this one. Bam, bam, and bam. Alright, and now we click done. Now, having these two, we can just first column bottom surf. We click it, we can see it. Column top surf. Click it, we can see it. Having this, we can just translate this one here. Select the instance to translate. Done. We can take this point and put it right here. Okay. Okay, very well. And now we can translate again this one. Done. And we can take this point and put it here. It's quite important not to make any mistakes. Might be a bit difficult to take it back if you manage to connect it. I mean, you can do it, but it's good to do it right first time. Click OK. And now we can say go to constraints, double click, and we will have the constraint column to column, and this will be tie connection. And we continue. Choose the master type surface, and we will have the master type, let's say column top surf. Continue, and choose slave type surface, and the slave type will be column bottom surf. And we click continue. This thing appears, and we leave it exactly as it is and click OK. OK. Now, maybe it's a good moment to save, so we'll just click save. What we will do now is that, let's see, column. If you click it, this thing goes with pink. So we might think that we have done a good job. Okay. Even though something looks with some dots here, but it's because yes, it's because the embedded connection here. But actually, we shouldn't have embedded this one here. We should have embedded everything at the beginning. So what we will do, we have here embedded rebars connection, and we will just delete it. Delete the connection. Okay. And for the moment, this is the way it will go. Very well. But the column-column connection, we keep it. This one is very good. Very, very well. Very well. Now, because you could have seen there was the connection here, the embedded connection here, and nowhere else. So we have to do it everywhere anyway. So let's just delete it everywhere for the moment. Yes. Now we can define the partition planes, just like here. Just like here is what we will do right now. Is this step over here. So, partition planes. We go to the assembly module and select the partition plane, defining cutting plane, select cells to partition. And we want first to partition these cells, done. And let's define it by point and normal. This point and this normal to the point. Create partition. The cell could not be partitioned. Try another partitioning strategy. No problem. We will just select it again, done, and choose 3 points this time. And we will have this point, and the third point, and create partition. And now we can go. Now we're talking. Now we're talking. Again, create partition plane, select this, done, point and normal, no, 3 points. And we choose this point, and the third point. Create partition. Very well. We go again, select the cells to partition. Every time we read here to see the state where you are. Select this, done, 3 points, zoom, 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 first point, second point, here, select the second point. We go here, select the second point, select the third point, we go here, click, and create partition. And we go back to our view, we go back to the side view, and it looks like we really did a good job so far. Now we can define the regions for the ties between the columns and the beams. And now we really have to do some clicking because there is no other way. So, good moment to save the work process. We just click save and we go to constraints, but not yet because first we have to define surfaces. We go to surfaces, name, and we defined one surface, column lateral surface. And of course, column lateral surface will be the lateral surface of the column that will get connected to the beam. So obviously this one, not this one. So we take, how many do we have to have? We need to have 1, 2, 3, 4, 5, 6. Multiplied by 4, so 24. Maybe I'm wrong, but let's see if we get 24. 1, 2, 3, 4, 5, 6. We go here. You remember to hold shift. 7, 8, 9, 10, 11, 12. $13, 14, 15, 16, 17, 18. 19, 20, 21, 22, 23, 24, and done. And we have column lateral surf. We click it, we can see it, very, very nice. Let's make sure again that we have a sign, the correct surfaces. So we just, come on, we just scroll around a bit. You do this kind of motion by clicking the left click and holding Control and Alt in the same time, if you are wondering how to do it. And it looks pretty fine. You can just go to this view over here and define another set of surfaces, which will be beam lateral surf. Continue. And we'll have 1, 2, 3, 4, 5, 6 multiply by 4, and it better be 24 as well, because it's pretty hard to connect 24 surfaces to 25 surfaces. So here 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. Very well, we are done. We can refresh the view and we can go to beam lateral surf, and it seems like we have done a pretty good job. It looks exactly like we want it to look, and now we can put it where it should have been from the beginning. Okay, so what we will do now is we will go to this view over here. We'll click translate instance, select this and this. Remember to hold shift, done. And now go to the side view, and we better make sure that we choose the right starting point and ending point to do this this final very important process of translating. So let's choose this point over here as a starting point, and as an ending point, this one here. We don't click OK yet, we make sure everything is alright, but keep in mind that we didn't click OK so far. Everything looks good. Click OK. Go back to our zoom. Looks pretty great. And we can save the process. Save. Alright, not bad. We have a structure. What we will do now is that we will embed the rebars in the concrete. And you really have to bear with me right now. Just let me have another sip of water. I will go under the instances, and what I will do is that for a moment I will suppress all the concrete. Yes, exactly, I will suppress all the concrete. So I click the concrete beam, then I click again here on the concrete beam by clicking on control. So I have control click here, and then here I have shift click. I have rebar, rebar, rebar. Here I have control click, control click, control click, or shift click. Here it doesn't matter. I go again, I have control click, control click, control click. you'll see why this on control click and shift click is important. I go again, I go again, I go again, I have rebar, 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 and I have here control click, concrete, 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 and here shift click, and I have now right click, suppress, and now we can see our reinforcement. How nice. What we will do now is that we will define a set, and we will name the set rebars. Yes. Continue. Rebars already exists and cannot be overwritten. Okay, it doesn't matter. It doesn't exist anymore. Or we will just go to this, select geometry for the set. And now done. And now rebars, we have all the rebars. And that's how we will embed it. We will embed it properly. Alright, alright. And we will go now and just resume everything. We will go select all and resume. And we could embed it in the whole model, but I don't really want to embed it in the whole model. I just want to be specific and embed it in the concrete. So what I will do is I will resume. I just suppressed everything. That's all right. I will select again the concrete. Concrete, 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 concrete. I have to have no concrete which is unselected. Concrete, 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 concrete. Okay, I will resume this, and then I'll create another set, and this will be concrete. Concrete. All right, continue, and select the geometry for the set is the concrete. Done. Very well, and now we have our sets. We have the rebars, which fairly don't appear here because they are suppressed, and the concrete, which is this one. Very well. Now we can just resume everything, not suppress everything like we did last time when we wanted to resume everything, but it was fine. So we're going to resume. We have this. We can just collapse everything here and sets the concrete set and the rebar set. Good. Now we can go to constraints, first we do something that we needed to do before. We will do column to beams, which is a tie connection, and we continue. Select the master type surface. The master type surface will be defined as the column lateral surface. Continue, and choose the slave type. It will be also surface, and we will choose the beam lateral surface, and we're gonna click continue and click OK. And here normally if you don't get any errors that the surfaces don't match or don't fit or something like that, it means that you have a correct geometry from this point of view of tying. And now the last tie that we have to do right here is that we have to embed the embedded rebars. We're gonna keep the name as we wanted to give in the beginning, and this will be embedded region, and continue, and sets may contain. Select the embedded region set from the dialog. The embedded region will be the rebars. Continue, Select method for the host region. Select region. And the host region will be the concrete. Continue. And here we will leave it as it is and click OK. Very well. Very well. We are gonna click save right now. And what I will do is I will start my cooling fan working, because even if you hear some sound from my fan, my computer is quite hot right now, so I'm afraid I really don't want to lose everything. I mean, I will not lose it, but I will not lose the work in ABAQUS, but I might lose the video, and I don't want to do it again. So you might hear some but yeah, we will deal with it. Okay. Very well. After exactly 1 hour, we have this model here, which is quite nice. Took me much longer first time to do it. But now we have to define, yeah, let's just define the gravity load. Doesn't hurt. Oh, yes, it does, in fact. Because what we will do is define our step. And the step will be dynamic implicit. Procedure type will be general, dynamic implicit. And we will name it earthquake step. Yes, and just continue. Time period. Okay, cancel. We don't define the step yet. We define the amplitudes. And we will name this Vrancia north-south accelerogram. And will be tabular. And we just click continue. Step time. Okay. And what we will introduce here is that from this Excel file that I said that you will have it in the description, I will just make a Dropbox public link. And if the link doesn't work, you can just leave a comment and I will make it work, or just re-upload it. The Vrancia is the Vrancia earthquake was an earthquake in Romania in 1977, and this is the north-south accelerogram, so the accelerations of the ground on the north-south direction, which are given by this. You have time here and the acceleration here. So this is the real earthquake, how it was. But what we will do is that we squeeze up the timeline by a factor of 10. So you see here you have 35, here you have 3.5. So this is what we will introduce in ABAQUS. So we will introduce this. You have 0.02, we will have 0.002, and so on, just to increase a bit the response of the structure. Maybe not, but you can just use any accelerogram and numbers that you want. This is just the working procedure, so you have an idea how to do it, then you know how to do it. You can use any structure and implement any accelerogram that you want. All right, so we just select all this here up to the end. By the way, if you want to select up to the end in Excel, you hold Control Shift down, and now I can click Control C, and I go here and I have paste. So now we created our tab with the amplitude data in acceleration. Baseline correction. Baseline correction, we don't do anything here, and we just click OK. Now we have our amplitudes. All right. Now we can see here in our amplitude step that it goes up to 3.51 seconds, right? Okay. So we create our step right now that we will name earthquake step, which is dynamic implicit. We'll use the Newmark method for for solving the equation of motion. Just if you want to find more about that, you can write in the comments and I will try to explain you. And just click continue here. For the time period, we will write 3.51. And for the incrementation, we will write the initial 0.002 and the max and the minimum 1.005. And for the incrementation maximum, for the maximum number of increments, we will write a big number. We will write 351,000. So we say that even if for every step we will use the minimum increment size, we still want to finish our earthquake to do the analysis for all the steps. So if we use just the minimum step, which will not happen, but with this number here, we are sure that we will get through all the steps and the analysis will not be stopped for this reason. Yeah, so by having this, we can just click OK. And now we can go to the field output request. And we can say that we want every 10 increments, but it's by default every 10 increments. So we're just gonna leave it like this. We click OK. See, you can check whatever is selected here: stresses, strains, displacement, forces, reaction, contact. We will leave this like this as well. Whole model, every n increments, 10. Okay. And now we will go to loads, double click loads, and we have first our gravity load. We can write here gravity load in the earthquake step, gravity, and we click continue, and we will write on component number 2, which is the y-axis, minus 9807, which means that the gravitational acceleration is 9.807 meter per square second. Amplitude here remains instantaneous, and we click OK. Again, we work in millimeters, Newton, millimeters, second, ton, Newton, millimeter, second, ton. So here we have to write in millimeters per square second, so it has to be like that. Okay. Then we have boundary conditions. We have some fixed support, displacement, rotation. Yeah, we go, continue. We just select in the viewport. We have fixed support for this. Remember to hold shift, this and this. Done. And for direction, let's say that the x-axis is east-west and the z-axis is north-south. So we want north-south to be our earthquake, but on x and on y we want to keep it 0. So on x is 0 and on y is 0, and on z we will have our earthquake. Okay, so we have fixed support, and then we will have moving support, earthquake step, continue. And actually we don't continue because here we are gonna write velocity slash angular velocity, but not exactly, because we don't use velocity, we use acceleration. So we will write acceleration slash angular acceleration, continue. we will choose the same areas here. 1, 2, 3, 4. Back to our view. Done. And we have a 3. And we have Rancha north-south acceleration, which we select from here. Yes. And here we will write 1000, which means that here the numbers were in meter per square second. This is the accelerogram that we use, meter per square second, but we want to use millimeter, so we multiply by 1000. And I want to multiply again by 100. So I write 1000 followed by 2 zeros, because I really want to destroy the structure. I want to see how plastification occurs in the joints or around the joints. I really want, I don't want to see what stresses does the earthquake cause. I want to see getting completely destroyed. But of course this is just an exercise to understand the procedure and to see some results and to basically see how to define the earthquake and implement it in ABAQUS. Yes, and we will have here at the end 100,000. Again, 1000 to transform meters into millimeters, and then another 100 just to have crazy big stresses, to have an impressive result in terms of stresses and displacements. Okay. And okay, and we can see here that we have some displacements here on this axis. Very, very nice. We can go here, and then we can save. And after we did the save, we can think about what do we still need to do. And what do we still need to do is to mesh the structure. And to do that, we need to, I'm just thinking right now if there's anything else except for meshing the structure that needs to be done. And I'm thinking, and I'm not finding anything. So let's just go to the mesh right now. Oh yes, I think I found it. We have to go to the property module. And what we need to do here is that we forgot to define the orientation for our beam. So we are here in the property module, and we go to assign beam section orientation for our part, yes, and we have select the region to be assigned a beam section orientation, and we select it and we click done, and we just keep it by default like this and click OK, and click OK again. Okay, very well. And now we have to go to we can go to start doing the mesh, and we can go to open the mesh module. Open the mesh module in our assembly, and we can see that we can have a really beautiful mesh with just hex elements. Green means that you can mesh with hex elements, which are 8 nodes solid elements, which is very good that you can do that, because if you can do that, and the analysis will go much faster, which will not be fast at all, but it will be much faster, instead of tet elements, which are tetraedric elements. But right now we would like to mesh the rebars first. So we have two, and unfortunately I think we have to do the thing with suppressing the concrete again, but let me just think a bit in the beginning. Maybe not. If I want to mesh, we have a set, right? We have the sets here. Sets, rebars. Okay, we have the set rebars. And I want to mesh seed instance, and I want to seed the sets. I cannot. Select the part instances to be assigned global seeds. Okay, so I cannot. So what I will do is that even if we might need to assign the boundary conditions again, we need to go again through this process. We want to suppress the concrete. Concrete, control, shift. Concrete, control, 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 control. Find a smarter method. Just find a smarter method and write in the comments below what method do you use to mesh the rebars in this situation. But I think this one is quite smart because we use this control shift trick, so you don't have to select everything, and it doesn't take that much actually, even if it seems a lot. You just here control click and here shift click, and you will right click suppress, and you will have the rebars. So now you can seed the instance, and you can just seed all this. Done. And we will just leave it by default 280. So for each beam we will have 10 elements, and it's alright. We will just leave it like this. We will click OK. Yes, and now we are done. And now we can do it. We can put it back. We can click resume. Yes, and now let's see if we still have the boundary conditions. Yes, we do. Or do we? Yes, we do, because otherwise we would have got some warning that the region does not exist anymore. And I was a bit worried that since we suppress and resume again, it might not work. But it works. So if you define boundary conditions and then suppress the regions where you define boundary conditions, and then resume them again, your boundary conditions will be fine, which I'm sure is not valid for mesh. So if you mesh and then you suppress and resume, the mesh, believe me, will not be there. So it's important to do the mesh. At least what I do the mesh the last thing. So the very last thing that I do is the meshing, and the second last thing that I do is defining the boundary conditions. Okay, so the boundary conditions are fine. So our rebars are meshed now, so we want to mesh the concrete. So what do we want to do? We want to select the whole model to say the mesh, or just select the concrete? Let's just select everything, because I think it's fine, because the rebars cannot be meshed with hex elements anyway, so nothing will happen. So now what we will do is go to the mesh module, and we will go to mesh, seed instance. We will select everything. We will click done. Approximately global size will be 75. So we will have 4 elements. 75 multiplied by 4 is 300. 75 multiplied by 2 is 150. Multiplied by 2 again is 300. So we will have 4 elements for each section of column or beam, and we will click OK and done. And now we have the seeds, and now we can click mesh instance, select the part instances to be mesh, and we select everything and click done. And then click done again. And it doesn't look as we want it to look. Maybe to do it again, mesh instance. So again, mesh controls, select the region for the controls, this one, done. And we have the green one, structured hex, okay. Seed instance, part seed, done. 75, alright. Apply, okay. And now mesh instance, select part instances to be mesh. It's this one, and done. Yes, and the problem is that I don't see any mesh, which is quite weird. Oh, okay, okay, my bad, my bad. This little button here, this fixes everything. Okay, so it's a very good moment, crazy good moment to save. And this is our model. And what we will do now is start the analysis. Oh man, I'm really happy about this model. I hope that the mesh in the rebars is still alright, but I think it is, and we will get a warning anyway at the beginning of the analysis if something is unmeshed. So we double click jobs. We will say Vrancia north south, and let's just say something else. I don't want to interfere with some other jobs that I have, so I will write YouTube. Vrancia north south YouTube. This is the name of our job. So I'm gonna click continue. Invalid name. That's alright. It's gonna be just like this. Vrancia underscore n underscore s underscore YouTube. I'm pretty sure I don't have this job named anywhere in this folder. So I'll click continue, and I will not change absolutely anything here, but you have some memory that you can specify here, but I'll just leave it at 90%, and hopefully my computer will not explode in the following 30 hours that I expect that the analysis will take. Yes, 30 hours, yes. And hopefully see you after 30 hours. 30 hours for me, 30 seconds for you, 30 seconds for you, maybe, lucky you. And just leave everything like it is, and click OK. And before starting running the analysis, I just want to tell you one more thing, that the earthquakes, normally they have the accelerations on all the directions defined, and I can find it here somewhere. For example, you see, this is the acceleration for Romania's 1977 Vrancia earthquake accelerograms. So this is north-south, the one that we use, but they also have east-west and up-down. And this is another earthquake from California in 1940 in El Centro. So these are other accelerograms for north, south, east, west, and up, down. And these accelerograms are public. Normally, we just have to find them, find the station that was in charge at the moment with recording the accelerograms, and you just get them from their website, or simply Google them for the earthquake that you want. It shouldn't be a problem to get them. Yes. So. You see, you can also have the east-west and up-down, which is here for us. North-south is Z, and east-west we said is X, and up-down is Y. So what you can do here is create other amplitudes, as we have for north-south. We can name Vrancia east-west acceleration and Vrancia up-down acceleration. You see. And what we can do with that is that we go to boundary condition, and instead of having fixed support on these two directions, these are displacement rotation, we can also name this two, or each of them, acceleration on a type, and define it according to their amplitude. So we can define on the whole free direction. But I don't have a supercomputer again. So maybe you do, so you just now you know that you can define the accelerations on all the free directions. But for this exercise, we will keep X direction and Y direction 0, and we will apply north-south acceleration on the Z direction. Okay, I hope you got the last thing that I said. And now we are gonna save again. We are gonna go to Vrancia north-south YouTube, right-click, submit. The following constraints are applied to regions that have been either deleted, renamed, or suppressed. which is not good at all. Do you want to continue submission? No, I don't want to, but I can see that I have some planes that are missing. I have some cut planes that are missing. So what I want to do, no, I don't want to. I don't want to continue. So what I want to do is go to my partition planes, which were somewhere here. They have to be somewhere here. Just go to position constraints. I know I had some problem finding them at some point, but they are here. They are here somewhere. We will find them. Column. Feature. Okay, you see here you have features, and these little bastards here, they were suppressed, so we will just resume them, and now it's much better. I go to the mesh again, see if all looks right. So it doesn't look right because we introduced that. So for some reason, before doing our meshing, these partition planes got suppressed here. So pay attention before doing your meshing that you have your partition planes, so you don't get something like that, right? So now what we'll do is we go mesh, just instance, select everything, done, and there we go. And now if we go again to the assembly model, you will have the partition planes. Okay, and if you go to the constraints, you have bin column constraint. Very well. You have column constraint. Very well, and you have embedded rebars. And unfortunately here in embedded rebars, at least part of the region concrete, which is associated with the region to which the selected interaction is applied, has been suppressed, deleted, renamed, or excluded, or is a part of the reference representation. And this happened because when we selected the embedded region, defined concrete, the partition planes were not defined yet. So yes, so we did the embedment too early. We should have partitioned and then, but we can still fix this right now. And this is, I think, the last thing that we need to do. So what we will do is that we click here, no, press yes to continue editing the interaction or no to cancel. We will click no. So embedded rebars, we have a problem, right? Right. We will delete this constraint for the moment, embedded rebars. Delete. Yes. What we will do now is go to sets. We have our sets. Rebars, which is alright, but concrete, which is not alright. We see, we don't have everything here. So we will delete the set concrete. Delete. Yes. And we will define it again. And we go here, and again, we will suppress the rebars. Now pay attention to suppress the rebars. Rebar, shift, control, rebar, shift, control, shift, control, shift, control, shift, control, rebar, shift, and that's it. Now we will suppress the rebars, but just to make sure we suppress all the rebars, so we go rebar. We suppress all the rebars and only the rebars, but only the rebars, it's easy because we will see a concrete element missing. Rebar, just not to leave anything. Okay, we suppress it, and now we will define a set. We go to sets again. Sets, double click on sets and write again concrete here and click OK, continue, and now we can select everything here, and this is the right way to define the set. Done. And now we have the set concrete. Now we can go here, click, we go at the end, shift click, resume. Now we have everything here. Okay. We just collapse this. And we go again to constraints. Constraints. Where are you, constraints? Right here. Double click. And we have finally embedded rebars. Embedded region. Okay. Select the embedded region, but we have sets. The rebars is our embedded region. Continue. Select method for host region. We select the region and we have concrete. And now our region is, after we click continue here and just accept default values, embedded. And now let's see what happened with the mesh. Oh my, we have the mesh. We suppress the concrete and then we put it back. And we have the mesh, which is totally not true, because in fact we suppressed the rebars and we put it back. So now we don't have the mesh in the rebars, but the boundary conditions should be good. Yes, they are. Yes, they are. Okay, so now we have to fix the mesh in the rebars, and I will just show you, because if we suppress this and then resume it, and then we go to the mesh, okay, we don't have the mesh here. And I did this because we needed to suppress the concrete again anyway. So you see, you suppress, you lose the mesh. We will suppress the concrete, shift, control, shift, right click, suppress. We have this, we have mesh, seed instance. We want to seed this instance. Done. It seems like it's alright. Just to be sure. Done. The value here was 280. Okay. Some part or instance meshes will be invalidated by seeding changes. You may either delete the affected meshes or cancel the part seed operation. Delete meshes. Okay. So now we have seed instance. Done. 280. Apply. Okay. And then we go to mesh. Instance. Select everything. And done. And now it should be meshed. Should be fine now. Now we resume the concrete. And we lost again the partition planes. This is unbelievable. So I will just resume the partition planes again. What a mess, but we will get to it. We will just mesh it here normally. Mesh everything. Seed instance, we are gonna seed everything. Done. We choose approximately global size 75, apply. Delete meshes, 75, apply. Okay. Mesh, instance. Select instance, this is the instance, done. And it looks like this, very nice. And then we go to our assembly model. We have the partition planes, we have the boundary conditions. Yes, we do. So we run the job. Let's see what we get. Submit. Submitted. We can click monitor and we can just check a bit in the beginning if it's working. See what happens. Got a warning for type error. Adjusted nodes with very small adjustments were not printed. Specify preprint. Don't really remember this warning before, and I wonder what adjustments did we do for the type errors, because we just simply put surface on surface, like perfect match. I'm just trying to see if we get some numbers here, and then I will stop it and retake the video after the analysis is performed. Okay, looks like it started. Not going too fast though. I hope 30 hours will be enough, but I still wonder about these two warnings here. Specify preprint model equals yes for complete printout. Actually, I don't know if we get some results this time, because I can see the increments, they are going really low, so maybe the analysis will stop because the increment is too small. Which is such a shame, but I really don't remember why do we have these errors right here. Or maybe it's working, maybe just... But I can see that the increment here got to 8 multiplied by 10 power minus 5, and if it goes below 1 multiplied by 10 power minus 5, it's over. And the time, the time here is 0.0005 seconds, and we have to go up to 3.51 seconds. Yes, that's where we have to go. So let's see. We got soon we will get to 1 divided by 10,000 of a second. 1 divided by 10,000. Right now it's... Oh no, we got actually to 1 divided by 1,000 of a second. And we will need to get this process 3,500 times. So we do... And how long did it take so far? Let's say it took 3 minutes, so 3,500 multiplied by 3 minutes. This is 10,500 minutes divided by 60, 175, divided by 175 hours. No, I don't think it will take 175 hours. I don't know, because you see actually right now it's even more. It's even better. So hopefully it will be fine, and I will see you in 30 hours. So I will stop the video and and we are back after exactly 30 hours actually, so our estimations were pretty good, and it's time to see some results. We can see here we have completed, just between brackets next to our job name, and actually I checked for last time I did that, and these two warnings were still here, so I guess we will just not consider them for the moment, so I don't think they're that important in our results. And we can see here for the total time we have 3.51 seconds, so we went through all the steps in the earthquake. Now we will just dismiss this, and we right click on our job and click results. Yes, and this button here is to auto fit the view. We click it, and for the moment we select from this box we select S, which is stresses, and we select S22. So S22 is the stress against the y-axis. We have that like that. Another thing that we do is this button here, we select the legend range in the colors, we click it, and by default is on auto compute, but because the ranges is very high for the stresses in the rebars, we will not see anything for the concrete. So because we want to study more the concrete than the rebars, we will specify 25 megapascals here, and for the negative minimum we will write -25. Okay, even if in tension we will not go to 25, but we just want to have a symmetrically defined legend. And now we can click apply, and okay. And now we are here. So what we can do is to see some animation by clicking this button right here, animate time history. Click it. Yes, and you can see that the structure deforms during the earthquake, and we have the stress field S22 in this animation. And here, by clicking this button right here, you can monitor the time. If you click here, just below the animation generator, you have some animation options. You have slow to fast. Here is slow. Here is fast. We just leave it fast for the moment. And here in time history, you can choose the time increment, which by default is frame based, but we just go and say time based and write time increment 0.05. We apply and click OK. So this is the deformed shape during earthquake, and the field in color represents the stress, the normal stress. Okay, now let's see some results, and the results that we will look for is the stress strain pattern for this point, and this point. So we take an element at the bottom of column, at the bottom of the column 1 element at the bottom of column 2, and 1 element at the bottom of column 3, and we will plot the stress strain diagram for each of those. And afterwards what we will do is that we will superpose the three plots on the same graph, and we will use a different color for every plot. So let's do it. We can stop the animation for the moment, even if it looks quite nice. It's what we expected to. And we will go to this button, which is XY Data Manager. Click it. I will just delete whatever was here before. Delete everything. Yes. you will not have anything. So when you start, you just have a blank window and you click create. From here you select ODB field output. So you have to pay attention when you define your field output in the model here that I will not double click it now, but if you remember from modeling, if you go in the beginning of the video in the modeling part, you have to pay attention what you select there. But by default you can just click continue here, and by default you have the stresses and strain and the displacement selected. So what you want to select here is for the position you select integration point, yes, and you want to select from the strain components, which is the capital E, you select epsilon 22, and from the stress components you select S22. Okay, and then you click the element nodes tab, and here you will click edit selection, and you will go to this element here and click done. So this was the element that we choose, and we click save. XY data will be extracted from field output using default names. XY data are saved only for the current ABAQUS session. So basically he's telling us that we better save our charts, because if we close, even if we save our process, if we close and open again, then the diagrams will not be available anymore. So we'll click here OK. We can see the saving process in the bottom right corner. So we have to wait a bit so the program generates the curves here, generating 2 XY data curves for earthquake step from 317 frames. Yes, and just a bit left. Okay, and now it's 100%. So because we will have two other points or two other elements for which we will record the stress and the strain, we don't want to mix them up. So we will go here and write rename, and here is E22, so the strain 22 for bottom of column 1, and click OK, and S22 we click rename and we say bottom of column 1, and we click OK again. Now we just take the whole zoom, we click edit selection, and we take this element right here and click done, click save, we click OK, and now we have to wait again for the process of generating the XY data curves. And I don't have time to cut the video, but what you can do is just skip a bit, just hit the right arrow a couple of times until you see here 100%, and then you can just retake the video from there. 77, 78, 80, okay, just have to wait a bit. Okay, and now it's 100%. We can go here and do the same thing. We have rename, here we write bottom of column 2 and click OK, and then we go here, rename, and write bottom of column 2. OK. Alright, and then the last point, we click edit selection, we go to the whole view, and we go and take this element right here, we click done, and we click save. Okay, for the last time we have to wait for this generator to finish, and then we'll be fine to plot our stress strain diagrams for 3 different elements. One element at the bottom of column 1, one element at the bottom of column 2, and one element at the bottom of column 3, where columns 1, 2, and 3 we said that R was here is column 1, here is column 2, and here is column 3. And now it's done, so we can close this window or dismiss, and we will rename here E22 rename, and it will be, you see here you have element 264, and you don't know actually how the elements are numbered, so you might mix them up, which one is for the first column, which one is for the second column. So the best way to do it is just to rename it, and when you see it afterwards, you know what are you talking about. So here is bottom column number 3. Okay, and for the stress as well, we will rename and write bottom column number 3. Okay, now we take back our zoom and we click create, and what we will select right now is operate on XY data, and click continue. And here there is an option combine, which is you just have to click this arrow exactly 3 times in order for that to appear. So 1, 2, 3, and you have the last one here, and you just single click it. So single click from combine. And now you can just drag this to the right to see a bit better. And you have double click on E22 column 1. You just write a comma and then double click on S22 column 1. Pay attention, when you select the operator from this box, you single click, and when you select the data from this box, you double click. So now you can say save as, and the name will be ES bottom of column 1. So we will save it. Okay. Then we will just change here from 1, we will delete and write 2, and here hit here delete and write 2 again, and we will save it, and we will write ES bottom of column 2. Okay, and we will do it again for column 3. We just write 3 here and 3 here. We save it and we write ES, which is strain. In our case, strain stress, because strain will be on the horizontal axis and stress will be on the vertical axis. So here, bottom of column 3. Okay. And now we can close this window, and you see you have here XY data. And you will go and where you have ES bottom column 1, right click plot. And then on ES bottom column 2, you right click add to plot. In ES bottom column 3, you will right click and add to plot as well. Okay, we can close this window now, right here, the XY data manager. And now we might want to change some colors and arrange a bit the axis. What do I do? Because probably you have some small font for the marks of the axis. So you just go here, you select tick marks, and no, you just go to axis and you have a font here. So here I use 14, maybe you have 8 by default. So if you have 8, I like to use 14, apply and OK. And same thing on this axis. I go here, select 14. If you want to change the title font, you select here. I want to make it, let's say, 36. Okay, and the title of the axis will change, the font size. But I want to keep it 14, so I just click apply and OK. Now let's change the colors, because we don't want this purple, the green, and the very navy blue. So we will go this button here, XY curve options, and here we have the 3 lines of our graph. We go to the first one. We don't have any symbols. Oh yeah, we do have symbols. We have the discretization, the points that define our curve, but we don't want that, so don't click this. And the line for column 1 we will have the color blue, the line for column 2 will have the color red, and the line for color 3 will have the color green. And what I like to use here as a color is that I go to the RGB spectrum, and here I put red 0, blue 0, and for green I will just write 128. This is a color that I like to use. When I use three colors on a plot, I use blue, red, and this green with 0, 0, and 128 on the RGB spectrum. So I click OK, and now we can see we have this as we want to look. And if you also want to arrange a bit the legend, because probably you have it somewhere outside here initially, so you just double click it, you just go to the area and you have inset or offset. So initially by default this button is not ticked, this box is not ticked here, so I'm just gonna tick it, and now it's in the middle, and you can actually move it with the mouse whenever you want to, or play with these two buttons here. So here we'll do just fine. And the font as well, maybe you have 8 by default and you cannot see much, so I'm just gonna make it 14. Apply and OK. And this is our stress strain diagram. The blue line for column 1, red line for column 2, so the element of the bottom of column 2, and the green element of the bottom of column 3. And we can see that the strains are the highest for the bottom of column 1. So they are basically crazy high. We have here 0.15, so it's 15%, which is crazy high. Actually, now we can see that the earthquake that we defined really damaged our structure, because we have assumed that our ultimate strain for the compressed fiber is 3.5 per mile. Okay, so the concrete is not able to undertake any load if the strains become higher than 3.5 per mile. But what we have here is so here we have 5%. Yes, 5%, and maybe somewhere here we have 2.5%, and somewhere here we have 1%. But 1% is still too big because it's greater than 2.5 per mile, which is maybe somewhere here. Yes, but again, we don't have to worry, because the goal here was not to design a structure, but to understand the process and to understand how to model it and how to view some results, and then you will be able to do it for any structure. Steel structure, which is much easier to model than reinforced concrete structure. So you will be able to implement any accelerogram that you want. You can take the real accelerogram of the earthquake and just view the results that you get. And now if you want to save this picture, you just go to File, Print, and initially you have this button here checked by the printer, but I want to save it on a file, in a file, so I just take this box reduced to 256 colors. I like to keep it unchecked, even if we don't have so many colors, but I prefer to leave it like this. Yes, and here current viewport, here the first box checked like this, rendition color, format here I choose PNG options, I just don't change anything here. So here you select where you want to have your picture saved and give it a name. And I will not save it right now because I have already done it. So I'll just click cancel, but you can click OK and save your picture. Yes, and I will cancel here again. And one last mention regarding this graph, probably you have some gray background by default, yeah, so I didn't want that, so what I have done, I just double clicked somewhere, anywhere, and you have this fill here. Yes, and I don't like it, so I will just uncheck it, and now click dismiss. Okay, and now we have the stress strain diagram for our points, or more precisely our elements, not our points, because the points or nodes is what we will use right now, just to click to see the deformed shape again. So now let's see some, you will select U from this box, and from this box here, let's select U3, which is on Z axis. Yes, but now we have to go again to this box, to the contour options, to say again auto compute and apply. And now we can start the animation, and instead of having the stress, the normal stress field, now we can see the horizontal displacement on the z-axis. And what's happening here, for the reason for which it's going so slow, is that first time it's going through the earthquake, it assigns the color, the legend colors to each element, but then when it will go from the second time on, it will go much smoother, much faster. So that's why you could have seen that for the stresses it was going faster, because before that I had already done it. So when we have done it for the stresses, it was going smooth from the beginning, but now it's not going so smooth. But we see here 2.99, and it has to go to 3.51, and then when it will go again, it will go smoother. But anyway, this is the displacement field. If you want to say we had a stress field in our first animation, and the second animation shows our displacement field on the z-axis, because x is 1 for, if you want to go on x, you see u1. If you want to go on y, you have to check for u2, and on z is u3. Yes, and now you can see it's already starting going smoother. But here again, if you just click this box over here, yes, you can change the time increment, or you can make it frame based as it is by default, but I want to change it in time increments. So the reason for which I do that is that I know that the time step between the frames of my animation is the same, because otherwise when the calculations were computed by the program, the increment was not the same all the time. So that's why I like to keep it here time based, so the increment is the same for every frame of my animation, the time increment, and not frame based. I keep it time based. Alright, so you still have other options here. It's our viewport, and here full cycle, half cycle. I don't really do anything here. And here in the player, it's a loop or swing, and I don't want it to swing. When I check for eigenmodes, I can just swing, but now I don't want to swing because it makes no sense to have our earthquake going backwards. So loop means that it's just going to go from the beginning to the end and start again from the beginning to the end, and swing is beginning, end, then from the end to the beginning, and so on. Yeah, so now it's already going smoother, and you can see that the displacement with blue here, we can 8.3 10 power 1, so it's 83 millimeters. With blue here, at some point between 0 and 1 seconds, we have here blue. Yes, like this. So here is around 83 millimeters, so 10 centimeters, and then less as you go up. Okay, so we can stop the animation from here, and now what we want to do is to plot the drifts for each of our stories. We are going to close this window, and I'm going to tell you briefly what the drifts mean. So for a multi-story structure, the drift is given by this equation here. So it's the horizontal displacement up minus the horizontal displacement down divided by the height of the story. As you see in this graph here, in this picture, you have the horizontal displacement down, the horizontal displacement up, and the height of the story. And by applying this equation, you obtain the displacement drift, and the displacement drift is a pretty useful tool in designing multi-story structure subjected to earthquake, because then you will compare the drift for each story to some values given by the codes, and you will see that you are between the values or if you're not and you have to redesign. Okay, so let's do that, and for that we will click here, XY Data Manager again. We will just delete whatever we had here because we already saved the picture, so we don't need it anymore. So delete, yes, and we will create. We select ODB field output, continue. And now we don't want to have integration point, we want to have unique nodal that we select. And we don't want strings, we don't want stress, but what we want to obtain is U, spatial displacement, right here. And why it's spatial? Because there is another one which is rotational, so that's why it's called spatial displacement. We go to U2, and then we can go to our nodes, and click on Edit Selection, and we have one node here. Okay, and click Done, and save. Okay, and now we have to wait for this process to end of generating the XY data curve. So you don't need to wait. As I said, I will not cut the video, but you can just click the right arrow on the YouTube window, so it will just go forward and forward until you will see here 100%, so you can just retake it from there. Actually, I might cut this part because I see it's taking a really long time. We'll see. 35% and going. Yes, so just to explain a bit, maybe the steps, we will save the U3 component of this point, which we will name point 0, and then we will save the U3 component of this point here, which we will name point 1, U3 component of this point here that we will name point 2, and the U3 component of this point here that we will name point 3. And then we will go to operate on XY data, and we will just apply this equation here, where the HS we will use 2800, which is our height of the story in millimeters. And then basically we will do the same thing that we did for the strains and stresses, plot them on the same chart, and we will see the drift of each story. 53%. Maybe in this time I could tell you something about the stress distribution in our structure or on stories. You could have seen that the strains were by far the biggest for the first story. So that's why in very high structures or tall structures, it's common sometimes to build the first story bigger than the others, so it gets more flexibility by this, right? And also to avoid the shear failure. Obviously in our model we don't have any stirrups, but you can do it. You can just try to do the same model and just to put stirrups, and then to compare what to compare the response of the structure with stirrups and without stirrups. And what you're supposed to see there is that the strains are much lower when you use stirrups. But obviously you have to use stirrups everywhere because that's how reinforced concrete frames work. But what I wanted to say is that the stirrups normally for the bottom column are much closer one to each other. But this of course comes from some design consideration. You have to check what stresses you have there, and design the stirrups. Again, we are not using design here, so I just know based on experience as well that I have seen structures that a lot of tall structures in seismic areas that have the first story much higher than much higher, not much higher, but higher, taller than the other stories. And it's typical for the buildings that have shopping centers at the ground floor, and just apartment buildings for the rest, or at least this is what I observed, as I said in previous observation just around the city. %85. I really don't know what I will tell you when I will assign the XY data curves for the next 3 points. So I guess it would be quite useful to cut the video then, but I will just keep it for this one. So it's 87% now, and we wait to do 100%, and when we will do the same thing for the next 3 points, I will just cut it, so you don't need to wait for the generating process. I will not click them right now, but I'm just telling you about some buttons here. You have some toolbars, and you can choose your toolbars from the viewport tab, I guess. And this is a useful toolbar. You just select your view. So instead of just rotating around, you just click one of these views, and you, depending on what you want to see, you click one of these views, and it's quite useful. Yeah. Or here you can set also some user applied, some user defined views, and then go through them. When you want your specific view, just click one. You define view 1, and then you just click 1, so you have the view that you want. Yes. So now it's 99%, so it will be done soon. Alright, we have our point here, and we will rename it, and we will write point zero. But the problem is that we have selected U2 instead of U3, so it's alright. I will just click cancel, I will just delete it, and you can keep in mind whatever I told you during the generating process. And now I will go again, and I will select U3 because U2 is on Y, and we don't want that. We want U3 as we have here. So I'll just select U3 and then go to element nodes, edit selection. I will take this one, I will click done. Now I will click save, OK, and I promise I will not say anything, and see you at 100%. Now our x, y data for the point, this point here at the bottom of column 1 is complete. So we will go here, and we will rename it, and we will write U3 for point 0. OK, where point 0 is bottom of column 1, point 1 will be bottom of column 2, point 2 will be bottom of column 3, and point 3 will be top of the column 3. Okay, so now we just get our view back, we click edit selection, we have this point here, but we don't want that anymore. We check again, so it's in the middle, so we go here in the middle, select this point, click done, and click save. Okay, and see you after the generation is complete. Actually, I didn't expect for all this assignment process for the nodes, where you memorize the displacement field, will take so long, but it is how it is. So here just rename and point 1 capital P, preferable point 1. Okay, now we go take our whole view back and edit selection. We are here right now. We will go here in the middle, we click done and save and OK, and see you at 100%. And now we have point number 2 assigned, so we go here, rename, and we write point 2. Okay, and we only have one point left, which is point number 3, so we take our view back and we click edit selection and go to the middle of the column 3 on the top, which is right here. We click done and save. Okay. And now the U3 XY data curve for point number 3 is complete, so we will rename it. We write here point 3, we click OK, and we can proceed to creating the chart that shows our drifts. So what we do is click here, create, operate on XY data, continue, and here we will write between brackets U3 4.1 minus U3 4.0 divided by 2800, just like that. And we save this, and this is drift 1 or drift story 1. Okay, now we write here 2 instead of 1, and here 1 instead of 0. And this is the drift for story 2. Dismiss. Oh, we did it right. So 1. And this is the drift for story 2. So we save. Drift story 2. Okay, and for story 3, we write here 3. We write here 2. And we save, and this is the drift for story 3. Okay, now we can close this, and here XY data, you have drift story 1. We can close this as well, the XY data manager. Right click, add to plot, yes. Story 2, right click, add to plot, and story 3, right click, add to plot. And what you can do here is that, as we like to do, to move the legend somewhere else. Now we have the axis, you see they are with 8, and we don't like 8, we want 14. Not the title, but the axis. Here font, and we'll take 14, apply. And same for the other, okay, and same for the other axis. Font 14, apply. Okay, and here time and displacement, I have it from a previous time, but you just basically double click it and go to title and write here time, and go to the other one and write here displacement, and that's it. And the colors, as I said, I can see that it has blue by default for story number 1, again this button here, and the color is blue for story number 1. For story number 2 I choose red. Okay, and for story number 3 I choose my green, which is 0, 0 and 128, because this is the green that I like the best to see. And dismiss. And now we have our drifts, and you can clearly see that the highest drifts are for story 1. So now we will just save this picture, and we go to File, Print, and current viewport, first box checked, and we have color, print in file, select the file where you want to print it and name it, and we have drifts, YouTube. I'll just write a name, PNG, alright, okay, just to make sure, okay, okay. I will not reduce it to 256 colors, even if it doesn't matter right now, but sometimes it does when you have something like a how is it called, a stress field or a displacement field in colors on the structure. So I will just click OK, and now we have our picture. We go here, we have picture with our drifts, and a picture with our stress strains diagrams. Very well. So now just go back to our stresses. We go to S and S22 and start the animation by clicking this point here, this button here. We go back to our limits for our legend colors, so we write 25 and minus 25, apply, okay. We can also write, I'll just click it again, we can write 2.5 and minus 25 just to see what happens. And now the negative will just go to minus 2.5. Sorry, the positive will just go to plus 2.5 where you have tension, and the negative will go to, well, in compression, to 25 or minus 25. But the problem is here you have no idea where 0 is. It's kind of hard to find it. 0 is on orange. You don't really want that, you want to have 0 on green. So we will just write 25 and minus 25. That's why you don't write here 2.5, even if it just goes to 2.5 in tension, but you want to have it symmetric with respect to 0, so you can see the colors clearly and make a good estimation based on what colors are there. And we just click apply like this, and OK. Yes, so what you can do also here is that you can take a view like this, for example. Yes, and you can see the structure along z-axis moving, so z-axis is here, and here these two buttons are to turn on and off the panorama. So if I click here, there is no more panorama, so I just see the side view like that. Yes, and now to turn the panorama on, let's click this button and maybe take the, or perspective as it's here. I can see that it calls perspective and not panorama. Now if I click the general view over here, there is this tool, this button, activate, deactivate view cut. Sorry guys, I was just confused for 1 second, because the thing is that you don't compute normal stresses for wire type elements. That's why when we went to the steel when we had S22 here, so the normal stress, there was something really weird here with 10 power 27, and so here. And what you want to do is go to primary, S and misses, where they actually also show you the maximum and minimum stress for every frame of the animation. And right now you can just click on the cut button right here, and if you click the button next to it, which is View Cut Manager, you can right here 3363, which is 300 and 400 minus 37. 37 is the concrete covering from the extreme concrete fiber to the center of the reinforcement as we defined it. So we should be in our rebars plane here, but we don't see it yet because we have to change the color field. So we go here, contour plot options, this button right here next to the plot contours on deform shape. Yes, contour options, and we just leave it automatic as he wants. And you see here is 350 and the minimum 0 for full misses. So it's exactly how we defined it actually. And we just click apply. And now the concrete will be blue because everything will be less than 2.9 multiplied by 10. So everything is less than 29 megapascals for the concrete. The full misses stress for the concrete. And then for the steel, you see this very nice contour here. And let's click this. You can see the proper full misses stress field for the steel in this way. And what I don't know, I'm not sure how to do it yet, but I would like to know, maybe you know, just write in the comments if you know, how do I do so I can see only rebars? So I just want to see the stresses, the full misses stresses in the rebars. I don't want to see any concrete, just the rebars. Because if I go with this cut like this, it just cuts everything. So I want to keep the steel. I just want to see all the steel and no concrete. I hope you understood what I said. Just write in the comments if you know. Okay, so that's it with this button that I wanted to mention, and what can be useful for. If you select this plane in this animation here for the normal stresses, you can clearly see that at this point the structure fails. The first story fails in shear because this deformation of the first story is not recoverable. So again, pay attention when you see here around 0.6. When you see here around 0.6, this deformation will occur, and this is not recoverable. So the first story fails in shear. Again, 2, 0.2, 0.3, 0.4, 0.5, 0.6, yes, and now you can see this pattern here. And this is shear failure of the first story. Yes, and that's what I mentioned the solutions for, with increasing the height of the story. Yes, so increasing the height of the story for an extra flexibility, and also placing the stirrups much closer onto each other. Of course, this model has no stirrups that actually are not that hard to. It's not that difficult to define them, to model them. They are just some wires, and then you just describe them as square. So just some square wires with some specific cross section and material properties. That's basically what the stirrups are and how you could define them, and then you can just create one stirrup and create a pattern, so a linear pattern, and you just place them where you want to place them. So that's how it goes with the stirrups. But you saw how long it takes to, so 30 hours just to define the earthquake on one direction and with no stirrups. So imagine how long it would take to define the earthquake on 3 directions and to create the stirrups and just merge everything. But of course, this would be the most the approach that would be the closest to the reality. If you have the whole 3 components for the earthquake, it's a pity not to use them, but you need a very good computer in order to be able to do that in a reasonable amount of time. Yes, so that was it. That was my presentation, my video where I explained how to model reinforced concrete frame multi-story structures subjected to earthquake. So thank you for watching this really long video. I guess if you had enough patience to watch through all of it, then you and me might have the same hobbies. Yes? So if you have any comments or questions, you know where to leave them. And if you have a video request, you can as well write it down in the comments section. So that's it, and good luck in engineering, and see you next time.